If I say atoms are real, most people nod politely. Of course they do. We've all heard it. Atoms, molecules, electrons, it's in textbooks, cartoons, shampoo commercials. It feels obvious. But here's the strange thing. For most of human history, atoms were not obvious at all. They were a guess, a bold one. And for a very long time, even smart people weren't sure they existed. So here's the question I want to hold on to for the next few minutes. Just one question. If you couldn't see atoms, if you couldn't touch them, and if no microscope in your time could show them to you, how would you know they're real? Not believe, not assume, know. Because believing something because science says so is not understanding. It's just good manners. Now imagine this. Suppose someone tells you that everything around you, this table, your phone, your own hands, is made of tiny invisible particles, endlessly moving, bouncing, colliding. You might say, all right, maybe. But then you'd probably ask, where's the proof? And that's a fair question. It's the only reasonable question. Richard Feynman once said that if all scientific knowledge were destroyed and only one sentence could be passed on to the next generation, it should be this. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another. That's a strong claim for one sentence, almost arrogant. Why that sentence? Let's try not to take it on authority. Let's pretend no one famous ever said it. Let's pretend we're just curious people looking at the world, trying not to fool ourselves. So instead of starting with atoms, let's start with something much more boring. Let's start with a glass of water. You pour it on the table. It spreads. It flows. It doesn't sit there like a brick. Now you heat it. It starts to evaporate. It disappears into the air. Then you cool it enough, and suddenly it freezes into ice, hard enough to crack your teeth if you're not careful. Same stuff, same water. Three completely different behaviors. Now here's the quiet puzzle hiding inside that everyday experience. Why does the same substance behave so differently without turning into something else? You didn't add anything magical. You didn't change its identity. You just changed how warm it was. So whatever water is, its behavior must depend on how its parts move. Weight parts. That word slipped in there. Did you notice? We talk about parts automatically because our intuition already wants to break things down. We don't think water is one continuous solid essence. We imagine it has pieces. Not because someone taught us atoms, but because that's how explanations usually work. If a crowd behaves differently when people are calm versus when they're panicking, we don't say the crowd changed its soul. We say the people inside it are moving differently. So let's try that same logic here. Suppose water is made of tiny pieces, not necessarily atoms yet, just pieces. When they move slowly and lock into place, water becomes ice. When they move faster and slide around each other, it's liquid. When they move so fast they break away, it becomes vapor. That idea alone already explains a lot. But here's the catch. An idea that explains something is not automatically true. It just means it's convenient. So how do we test it? This is where Feynman-style becomes important. He wouldn't rush to equations. He'd say, all right, let's see what this idea would predict. If matter is made of tiny moving particles, then they should sometimes do things we don't expect at the human scale. For example, suppose you open a bottle of perfume on one side of the room. You don't push the smell across the room. You don't wave it. You just open the bottle. And somehow, a minute later, someone on the other side says, hey, what's that smell? How did it get there? The room wasn't windy. You didn't stir the air on purpose. So something must be moving on its own. Now you could say, well, smells just spread. But that's not an explanation. That's just renaming the mystery. Spreading how? If perfume were a continuous substance, like a ghostly fog that magically fills space, you'd expect it to smear smoothly and evenly, but that's not what happens. It spreads slowly, randomly, unevenly. which is exactly what you'd expect if tiny particles were bouncing around, colliding with invisible air particles, wandering in all directions like drunk pedestrians. Already, without microscopes, we're getting hints. But hints aren't enough. We want something sharper, something that says, if atoms weren't real, this would be very hard to explain. So let's keep pushing. Imagine a sealed container filled with gas. You heat it up, the pressure increases. Why? You could say, because heat causes pressure. But again, that's just labeling. Let's slow down and think like someone who doesn't know modern physics. Pressure means the container walls are being pushed. What's pushing them? If the gas were just a smooth, continuous substance, evenly filling space, why would heating it make it push harder on the walls? But if the gas is made of tiny particles flying around and crashing into the container, then heating it, making those particles move faster, would naturally increase how hard and how often they hit the walls. Same container, same gas, just faster motion. That idea doesn't just sound nice, it predicts exactly what we measure. And now something interesting happens. We're not just explaining one phenomenon anymore. We're explaining many with the same simple picture. Smells spreading, gases pushing on containers, liquids flowing, solids resisting deformation. One picture, many consequences. This is where a scientist starts to feel a quiet confidence. Not certainty yet, but something like, this is working suspiciously well. Still, a skeptic might say, all of this could be a clever model, a story. You haven't proven atoms exist. You've just shown that pretending they exist is useful. And that's fair. So let's look for something harder to fake. Let's look for a phenomenon that doesn't just fit the particle idea, but almost demands it. For that, we need to look at something that seems, at first glance, completely unrelated. We need to look at pollen grains floating on water. In the early 1800s, a botanist named Robert Brown was looking at pollen grains under a microscope. He wasn't trying to discover atoms. He was studying plants. But he noticed something odd. Tiny pollen grains suspended in water were jittering, not drifting smoothly, not sinking, just trembling, dancing, zigzagging randomly. At first, Brown thought they were alive. So he did the sensible thing. He tested that idea. He crushed the pollen, same motion. He used dust, same motion. He used particles scraped from rocks, same motion. Dead stuff, lifeless stuff, still jittering. So the motion wasn't biological. Then what was it? Here's where things get interesting. The motion didn't stop, no matter how long he watched, and it got more intense when the water was warmer. That detail matters, because warmth, as we've been quietly suspecting, has something to do with motion. Now imagine you're Feynman, or anyone with his style of thinking. You'd say, all right, suppose water is made of tiny particles we can't see. They're moving around constantly. Then what would happen to a slightly larger particle, like a pollen grain, floating in that sea of invisible motion? It would get hit from all sides, unevenly, randomly, sometimes more from the left, sometimes more from the right. The result wouldn't be smooth movement. It would jitter, exactly what Brown saw. And now the temperature detail clicks into place. Warmer water means faster invisible particles, which means stronger, more frequent hits. The pollen doesn't know about atoms. It just responds to impacts. This motion, now called Brownian motion, was later analyzed quantitatively, not with philosophical arguments, but with numbers. And those numbers did something remarkable. They allowed scientists to calculate the size of the invisible particles that must be hitting the pollen to produce the observed motion. And those sizes matched what chemists had already suspected atoms should be. At this point, the situation changes. We're no longer saying atoms are a nice story. We're saying if atoms didn't exist, we'd have to invent something almost exactly like them with specific sizes, masses, and behaviors to explain what we see. That's a different level of evidence. It's not a photograph. It's not a direct image. but it's the kind of evidence scientists love, consequences you can't easily escape. Let's pause here, because this is subtle and important. Atoms weren't discovered by someone finally seeing them and shouting, "Aha!" They were discovered the way detectives discover a suspect they've never met, by footprints, by fingerprints, by patterns that point to one consistent explanation. Feynman liked this kind of reasoning because it's honest. It doesn't pretend we have access to ultimate reality. It says, here's the simplest story that survives every test we throw at it. Now let's make this more concrete. Imagine standing in a crowded room with your eyes closed. People are constantly bumping into you. Light taps, heavy shoves, random directions. If someone asked, are there people in the room? You wouldn't need to see them. You'd feel them. Brownian motion is like that. The pollen grain is feeling the crowd, and the crowd is made of molecules. Now, someone might object, but wait, you're still not showing me an atom. You're inferring. Yes, exactly. Science doesn't work by mystical revelation. It works by inference, constrained by evidence. And the inference here is powerful because it connects things that otherwise seem unrelated. Heat, pressure, diffusion, random motion, chemical reactions, all pointing to the same underlying picture. But there's still a lingering discomfort, a kind of philosophical itch. You might be thinking, okay, but maybe matter is continuous and these effects emerge somehow without discrete particles. That's a reasonable doubt. So let's push the idea into a corner where it has to make a sharp choice. Let's think about mixing. Suppose you drop a spoonful of sugar into coffee. At first, the sugar is localized. Then, slowly, without stirring, it spreads out evenly. If matter were continuous, sugariness would have to flow like a dye diffusing through a uniform medium. But diffusion doesn't behave that way. The math of diffusion, which came later, assumes random walks, tiny steps, many collisions. And again, when scientists measured diffusion rates, they could infer the size and motion of the particles involved. Different substances diffused at different rates in ways that made sense only if they were made of discrete units with different masses. By now, the pattern is hard to ignore. Every time we ask, what would we see if matter were made of atoms? And then go look, the answer keeps coming back. Yes, that's exactly what we see. And when we ask, what if matter were perfectly continuous? The explanations start to stretch. They become contrived, ugly, full of special rules. Feynman had little patience for ugly explanations. He didn't think nature was obligated to be simple. But he noticed that when an idea keeps explaining many things without extra tricks, it's probably onto something. Still, let's not get carried away. Let's bring this down to your kitchen. Open your freezer. Take out an ice cube. Put it on a plate and leave it on the counter. It melts. Nothing surprising there. But think carefully about what isn't happening. The ice cube doesn't melt from the inside out randomly. It melts from the surface. Why? Because whatever holds the solid structure together is being attacked from the outside first. Heat flows in. Motion increases. Bonds loosen. If matter were continuous, melting would be a strange, abstract transformation. But if matter is made of particles arranged in a lattice, melting is simply the breaking of that arrangement. Now here's a subtle test. When ice melts, the water molecules don't change into different molecules. They don't get bigger or smaller. They don't lose their identity. Only their organization changes. That distinction between the identity of particles and their arrangement turns out to be enormously powerful. It explains why you can freeze and melt water over and over without destroying it. It explains why metals can bend without turning into something else. It explains why gases compress and solids don't, at least not easily. Now think about smells again. Open the fridge. Something's gone bad. You don't see it, but you know it. Those smell particles travel through the air, weave through obstacles, enter your nose. If matter were continuous, smells would blur instantly. Instead, they arrive gradually, unevenly. sometimes stronger, sometimes weaker. That randomness is a signature. Feynman loved signatures like that, behaviors that scream. There's something microscopic going on here. Now let's address a common misunderstanding gently. Some people think atoms are like tiny billiard balls, solid little spheres banging into each other. That picture is useful at first, but it's not quite right. Atoms are not solid in the everyday sense. Most of an atom is empty space. The forces between atoms are not tiny rods or glue. They're interactions. But here's the important part. Even though the picture is imperfect, the idea of discrete units remains. You can replace billiard balls with clouds of probability, electric fields, quantum waves. The details change as physics advances, but the core idea survives. Matter is not continuous. It's granular, like pixels on a screen. Zoom out, and you see smooth images. Zoom in far enough, and you hit the underlying structure. Now here's a fun mental experiment. Imagine a world where matter really is continuous. No atoms, no molecules. Could you have chemistry? Chemical reactions depend on substances combining in fixed ratios. 2 hydrogens and 1 oxygen make water, not 1.7 hydrogens, not 2.3. Why such precise proportions? Because you're counting units. If matter were continuous, you'd expect chemistry to be sloppy, variable, fuzzy. Instead, it's crisp. This was one of the earliest clues, long before Brownian motion was understood. People noticed that substances reacted in exact mass ratios, again and again. The simplest explanation? They're made of countable pieces. Now, notice something important about our reasoning so far. We haven't relied on authority. We haven't said, trust us, scientists, no. We've followed a trail. Everyday observations, simple assumptions, testable consequences, consistency across many phenomena. That's the Feynman way. And now, having walked that trail, we're finally allowed to do something we postponed. We're allowed to name the idea. The name for this idea is the atomic hypothesis, not atomic theory in the sense of dogma, hypothesis in the sense of a guess that earns its keep. The hypothesis says matter is made of tiny discrete units that move, interact, and arrange themselves in different ways. Once you say that out loud, an astonishing amount of the world suddenly makes sense. Temperature becomes a measure of average motion. Pressure becomes momentum transfer. Diffusion becomes random walks. Phase changes become rearrangements. Even sound becomes waves of particle motion. Now, here's where people often slip. They hear all this and think, so atoms are little solid things bouncing around like marbles. And then, later, when they learn about quantum mechanics, they feel betrayed. Wait, atoms aren't really like that? But that's missing the point. The atomic hypothesis is not a picture of ultimate reality. It's a statement about structure. It says the world has units. Those units might turn out to be strange. They might behave like waves, probabilities, fields, but they are still units. Feynman was very clear about this. He didn't worship models. He used them. If a model explains and predicts, you keep it. If it fails, you fix it or replace it. Now let's clear up one more misunderstanding. Some people think atoms were proven the moment we built electron microscopes and took images. Those images are wonderful, but they came late. Atoms were already doing real work long before anyone saw them. Chemistry worked, thermodynamics worked, statistical mechanics worked. Seeing atoms was like finally meeting a pen pal you've been corresponding with for years. Nice, but not essential. The belief in atoms wasn't faith, it was earned trust. Now let's test whether you really understand this, not just remember it. Imagine a completely different context. Forget water, forget gases. Think about traffic. Cars are discrete units. Roads are continuous. Traffic jams form not because the road changes its nature, but because the behavior of the units changes. Slow down enough, and the whole system behaves differently. You can model traffic flow with equations that look suspiciously like fluid equations, but the underlying reality is still discrete cars. Matter is like that. At large scales, it looks smooth. At small scales, it's made of individuals. Now flip the context again. Think about digital photos. A photograph looks continuous. Zoom in far enough and you hit pixels. The image doesn't stop being real because it's pixelated. Its realism emerges from structure. That's the atomic idea, stripped of physics jargon. And now, one last challenge. Suppose someone says, okay, atoms exist, but do they really matter for everyday thinking? Here's the quiet answer. Every time you reason about heat, materials, chemistry, or even biology, you're relying, knowingly or not, on the atomic picture. Enzymes work because of molecular shapes. Drugs work because of atomic scale interactions. Your phone works because electrons move in controlled ways. You don't need to visualize atoms all the time, but the rules governing the world depend on them. And that's why Feynman chose that sentence. Not because atoms are cute, but because that single idea, once truly understood, changes how you think about everything else. So let's come back to where we started. If you couldn't see atoms, how would you know they're real? You'd know the way you know the wind exists, or gravity, or time, by their effects, by the fact that pretending they don't exist makes the world harder to understand, not easier. The important thing isn't memorizing that atoms are real. The important thing is noticing how we came to know. We didn't start with certainty. We started with curiosity. We didn't demand perfect proof. We demanded honest explanations that survived contact with reality, and we stayed willing to be wrong. That's the deeper lesson here, not atoms, but a way of thinking. So here's something small you can do. Take one everyday phenomenon, steam rising from a kettle, sugar dissolving in tea, a smell spreading through a room, and try to explain it out loud using the atomic picture. Not with fancy words, with simple ones. If you get stuck, that's good. That's where understanding begins. And if you can explain it simply, without fooling yourself, then you're not just repeating science. You're doing